grab your cup of coffee, and I'm going to turn it over to Bryan, and we'll go ahead and get started with the DER session. Bryan.
Great. Thanks, Charlie. And thanks everybody for coming now. It's very exciting to see that the DERs have had a pretty big presence at the conference so far. We heard in the keynote this idea of how DERs are growing, and other presentations have highlighted how various DERs are, and even things like rooftop solar are in the 25% of energy for some select areas, particularly areas like California, not California, well, they're high, but Australia and Hawaii. Also, Charlie was highlighting early on the idea that, there's expenses, and right now behind the meter and customer sided DERs may look a lot more expensive than some of their commercial and industrial scale ones, and then even higher still to relative to the utility scale connected to transmission. But I also recognize in that same conversation, and Deepak's as well, hey, we never would have expected the transitions we've seen in the last 10 years if we looked at the way prices were for some of the bulk scale systems. So it'd be quite interesting to see how things end up in the DER space as well as look ahead a decade. Also, just a couple of little framing concepts. I know hopefully many folks here are already quite familiar with distributed energy resources, but a lot of times people are approaching this from a specific perspective. And it's easy to think, for example, we're just talking about behind the meter rooftop type solar or storage, but really it's important to think about this in a much, much broader perspective. We've heard about the demand response programs, there's industrial side of things. Even on the solar perspective, if you're 5 to 10 megawatts, you're probably going to be connected to distribution and look like a DER. And in fact, we're even seeing some of the larger developers starting to install things on the distribution side to avoid some of the queues you've heard about and some of the challenges, particularly in the US, with getting online elsewhere in the system. So, it's been fantastic. As I mentioned, so many different sessions we've heard from the virtual power plant side, as well as from the dynamic pricing in the last session. So this is kind of our round out of the main conference session of distributed energy resources. And we're talking about a wide range of different topics, everything from planning to operations down to individual customer levels within this channel. So very excited to be part of it. That last little plug is if you are staying around tomorrow for the working groups, there is also a distributed energy resource working group that Obadiah leads. There'll be a chance for some further discussion in this space and thinking about where ESIG might go in the future and further expand in the DER space. So thanks again for coming. And without further ado, I'm going to go ahead and introduce our first speaker. We have Greg Adams, who's a technical executive and consultant for EPRI. And he's going to be presenting to us on more on the planning side. So thanks.
Thank you, Brian. Everybody hear me okay? Okay. So I'm Greg Adams with EPRI. I represent the distribution operations and planning organization there at EPRI. And I want to talk to you today about integrated planning, but from a distribution energy resource perspective. How do we really maximize the value and optimize the value that we get out of those distributed energy resources? So I'm going to talk about the process. I'm going to talk about capabilities. I'm going to talk about, I'll touch on the data, some of the data that we need in order to really maximize that value. There's not a lot of studies out there that really dive deeply down into the distribution system. Most of them are at the bulk level. And when we're looking at these future states of the grid, in the 2040, 2050 timeframe. And so a lot of the distribution system gets neglected in these studies, but the ones that do look at the distribution system and take that deeper dive, and here's an example of a few of them. There's a consensus among those research efforts. And that is that there's value in optimizing across the bulk and the distribution system when it comes to resources. So just to set the stage, I want to talk about, this is a grid, right? You've got generation on the left and you've got the customers on the right. And you have distribution and transmission in between. You can see the T&D interface there. And the distribution is represented inside the blue circle or the blue dotted line. And then I've also got the orange circles there because a lot of things are happening inside those orange circles. We've got distributed energy resources, but we also have electrification going on. And with the electrification, what we're seeing is growth in energy density, right? Normally we see growth from population growth, and we see growth traditionally, that's what we would see. But now what we're starting to see because of electrification of transportation, electrification of heating, things like that, we're seeing increases in energy density. So that's impacting our supply chain all the way down to those service transformers. Now, overloading a service transformer, just one service transformer, doesn't have a significant consequence to it. But when you're talking about a lot of our utility customers, our utility companies out there, they have hundreds of thousands of these. So when we start seeing this kind of growth, the impact to hundreds of thousands of these transformers can be a significant impact. So common to just generation, transmission, and distribution, we're all seeing increasing complexity, and we're also seeing customer engagement, more customer engagement. We're seeing increasing peaks and valleys like we see on the duck curve. But what's unique to the distribution system is it's what connects to the customer. And there are exceptions to that, I get that. But that's an important link. Also, the quantity of equipment that we have down at the distribution system compared with the bulk system is significantly greater, right? The number of feeders, the number of miles, just the quantity of equipment, and we have very little visibility of that equipment. Another thing to keep in mind as planners is that as we transition to clean energy, there's three underlying objectives that we have to include in everything we do. We have to think about the integrity of the grid. And when I talk about integrity of the grid, that includes the reliability, the resilience, the things you see at the bottom of the screen there, but also the agility of the grid to adapt to our changing environment. There's also costs and the affordability that our customers see on their bills, and customer engagement. This last one you don't see in a lot of presentations, but it's important because if you think about what we're doing, is we're asking customers to electrify their heating. We're asking them to electrify their cars. We're asking them to cook with electricity. We're basically asking them to put all of their energy eggs into this clean electricity basket. And if that basket's not affordable and it's not reliable, that's the equivalent of dropping that basket. So how do you get value out of distributed energy resources? How do you get value out of non-wire solutions? And the way to do that is to recognize that the distribution system is a system of systems. Each of the micro systems, think of those as maybe the feeders, but even take it further down to neighborhood levels and down to the business centers, and realize that each one of those is different. They're like fingerprints. And so to go and try to look for solutions and peanut butter across the entire solution or the entire distribution system, some of it works, some of it's not going to work for you. So we really need tailored solutions. We heard a little bit of that this morning about the targeted solutions. And I like to use the word tailored because the lawyers don't seem to like the word targeted. But anyhow, I use the word tailored. These tailored solutions that are specific to those unique locations on the distribution system are very important. So that means putting the right technology in the right location at the right time. An example of that would be, take a look at this curve. It's a load curve for a southwest area like this one, where it's in the summertime, where it's hot in the afternoon. And so you end up with a peak in the late afternoon. So imagine that we have a specific solution, a solar plus storage, maybe an oversized solar array, a little bit smaller battery that helps us to flatten out the peak, fill in the valleys. And then you add to that managed charging. And what we've just done is we've deferred infrastructure by putting in some of these solutions, but we've also added revenue. All right, and by adding this revenue without having to build additional infrastructure, that puts downward pressure on rates, making our solutions more affordable. But we're not done, right? Because I just talked about value we're only going to get for a few hours during the year. That's during those peak hours of the peak day. So we need to look at taking those same kind of resources and how do we eke out a little more value out of each one of them. And so during the rest of the year. So that's looking at value both temporally and spatially. And you can get that temporal value by looking at ancillary services, arbitrage, backup, whatever gives you the maximum amount of value. By doing this, that enables you to maximize the value for each one of these solutions, improve the business case of them. So when we're talking about these non-wire solutions or DER, we're seeing we can apply those in a lot more locations on the distribution system a lot sooner. But we have to include all the value streams. You cannot do that using our current methods of planning. And so we need to look at new ways of doing that. So let me just talk a little bit about our current methods of planning. I'm going to go through this really fast. So this is a traditional annual planning process where on the left you have the customer programs and you have pricing programs, and that influences how people use energy. So that influences the forecast, and the forecast goes over to the distribution planning, and then it goes to resource planning at the same time. And they don't even need to talk to each other, right? They don't even interact. But meanwhile, transmission planning is waiting for the results of distribution planning and resource planning because they're in the middle. And so when they get their information, they can do their analysis. And out of this whole process, you get a whole portfolio of projects, usually upgrades to the system, and they negotiate, arm wrestle, and out the end, you get a prioritized list of projects. Not a lot of coordination needs to go on in this process. There's definitely communication, but not a lot of coordination. So imagine an alternative. And this is just one way to do this, okay? But imagine an alternative where you have an oversight group, where that oversight group represents the teams that I just talked about, but also external stakeholders and internal stakeholders. And they're establishing targets for things like budget, sustainability, priorities. And then meanwhile, you're gathering information, data, that including forecast data, that all goes into developing a study plan. And the groups you see on the right are the ones, those are the experts that are going to run the studies. They're developing the study plan, and they're looking at the data that they're going to use. They're looking at the assumptions they're going to make. They're looking at the scenarios that they're going to evaluate, and they're going to put that all together. And already that's a breakthrough where you're talking about all these different teams working with the same data. They'll run that by the oversight group when everybody's on the same page. Then the analysis gets done using the traditional models that we use today. But they come back to the table. And when they come back to the table, they may challenge each other with what they're seeing as far as the results are concerned, but they're looking for opportunities to optimize across generation, transmission, distribution, customer programs, pricing programs, whatever it might be. Out of this process, and I call that the agile planning period. That's where change can occur. That's where innovation occurs, opportunities for innovation. Out of this process, you end up with a portfolio of optimized projects and programs that get maybe checked one more time, and you end up implementing. So from a distribution perspective, what are the capabilities we need to do that kind of planning? And I've already talked about it a little bit, but the unique demographics, recognizing those unique demographics all the way down to the neighborhood level, business center level, at least down to the feeder level, and then using that information to create forecasts that are specific to those areas, each one with its own load shape, each one with its own peak and the timing of that peak. Use that information, but other information in order to create scenarios. And scenarios are really important, especially, excuse me, in long-term planning. And I'm going to touch on that in the next slide. Being able to measure the impact for any hour of the year, not every hour of the year, and not just the peak hour of the peak day, but for any hour of the year. And then optimizing, I talked about that on the previous slide, but the one I really want to emphasize is this last one. And for the first time, I've heard somebody talking about that this morning, is this idea of measuring these non-wire solutions, these DER solutions, and making sure that they're accomplishing what we need them to do. If they're not, being able to make adjustments to those programs so that they can do what they want to do. Why is that important? One is so that if they're not, we can fail fast, make adjustments so that these programs stay effective. But the most important part of that is to build confidence among the planners that these systems will work. And so we have to use data to show these planners that these solutions will work, and so that they'll put these tools into their toolbox when they're doing their planning. So this is showing a contrast between long-term and short-term planning, or mid-term planning. Short-term planning, I like to use short-term planning for less than a year, which you might see in more of the operational planning space. So I'll use long-term planning, mid-term planning. Mid-term planning is traditionally what we do for distribution planning. Now, they look from a high level, they look like the same steps, and they are. But when you start taking a deeper dive, that's really where the differences are. And you cannot use mid-term planning processes to do long-term strategic planning. The questions that you see in long-term planning they tend to be more strategic. The horizon is beyond 10 years, so it could be 20 years, it could be 30 years. And so forecasts are not going to be accurate. And so using scenario projections instead makes a lot of sense. That helps you to understand those risks. And then you use a more broad area perspective of the distribution system in order to do that analysis. It needs to be more efficient than going down there and looking at specific pieces of equipment like you would do in your mid-term planning. The outcome out of all of this is really to understand the consequences of your risks that you got out of your scenario projections, and then be able to make decisions based on those risks and the consequences of those risks. So they tend to be strategic decisions, like what do we need to do as far as upgrading standards? What do we need to do as far as upgrading our planning criteria? And the example I like to use is like in that service transformer in that little red circle. When do I need to start replacing those and upgrading those pieces of equipment? Your long-term planning methodologies will help you to understand that so that you can get them in your warehouse and apply them when you need them. In the midterm planning process, the questions are tactical. The planning horizons tend to be much shorter. You're actually using real system forecasts and allocating those down into distribution systems, studying specific impacts, and your mitigation solutions tend to be projects for infrastructure. But the example that I just gave you for the service transformer, our forecast won't take us down to that level of granularity. I can't tell you when that transformer in my backyard or on the pole is going to be overloaded, but we can monitor it using aggregated data from our AMI information. When we see the overload based on the information, whatever criteria you want to decide that overload is, then you create a work order and you do the work when you got time. Things not going to blow up right away, right? So you do it when it's convenient. So after doing this a couple of times, these are some key insights that I jotted down. One is that difference between midterm planning and long-term planning. You need both, requiring a deeper understanding of the customer and their propensity to adopt technologies and their behavior in these various programs, as well as how we can influence behavior. Heard about that this morning too. And then improving the modeling so that it becomes much more efficient and so that we can do more of those iterations and optimize better down the road. And then finally, recognizing that modernizing the grid is an important enabler. It's important to give us the visibility that we need to do planning, but it's also important so that we can operate the system as planned and control, so the visibility and control. So that's part of that grid modernization. So I think that's my last slide.
Fantastic. Thanks, Greg, for leading us off with a great introduction and also staying well on time. Thanks much. Our second presenter today is Tom Breare, who's the Global Head of Partnerships at Kraken, coming to us from the United Kingdom. So thanks for making the journey. He's going to be talking to us today about harnessing the power of customer flexibility.
Thank you, and thank you to ESIG for inviting us along to present today. So I wanted to talk a bit, apologies in advance, it's a bit less of a technical presentation, more of kind of an overview in terms of how consumers can, how we can shift that mindset of consumers being, you know, a potential problem to the energy transition, to how we can take them on board and make them be part of it. For those of you who don't know, just a very quick overview of Kraken, given that we are a UK-based company, we operate now across all regions across the globe. We're a technology platform that covers all of the different areas of the electrification space, from supply, generation, storage, and networks across our different products. And I'd be happy to speak to anybody about it. So the energy system's been incrementally improving for the last 2 decades. We have seen a increase in time. We've seen an increase over time of renewables being built onto the grid, led by government subsidies. We've seen an 18% compound annual growth rate and 7 times growth over the entire period from 2010 to 2022. And we've seen this has been, you know, in the UK alone, we've seen 47 gigawatts of new capacity being installed, and we've seen some of the grids operating today at close to 50% at times renewables on the grid at any one time, and increasing levels of and the Nordics hitting somewhere up to 70 to 80% of this as well. And at the same time, we've seen the cost of renewables coming down as more and more renewables and storage have been deployed. The cost of these has come down. Early projects take time and costly at first, but as we start to build these out, we become better at scaling and bringing down costs. Back in 2004, it took almost a year to install a gigawatt of solar. That came down to a month in 2016. In 2010, a week in 2016, and a matter of days in 2030. There's a German utility who posted an advert back in the year 2000, which effectively said that renewables could only do about 4% of demand in Germany. This is now sitting up at around 50%. Similarly, a Norwegian study predicted the global scale of wind and solar would saturate around 1.71 terawatts in 2030. We're halfway to 2030 from when that report was first produced, and we've already surpassed 2.17 terawatts on the grid. But we're now moving into the new era. We're moving into the consumer era, and we need to take a further step. We're moving into a world where rapidly utilities are no longer in control. Generation is no longer taking place simply at the larger scale. Utilities are not deciding where generation is going to be input. Instead, we're seeing an increasing amount of technologies taking place and being installed, generated, and consumed at the grid edge level, where we have greater visibility. And this is happening quickly, and it's a problem that we're going to have to deal with. In a similar way to the triple jump, this is Yulimar Rojas, who is the current Venezuelan triple jump world record holder at 15.74. We've done the step in subsidizing renewables. We've done the hop in bringing down the cost of it, and now we've got to take that large jump into the consumer era. But demand is changing at the consumer side as well. This is a typical energy usage curve that we've typically seen previously. A fairly flat usage curve, peak in the morning, steady increase in demand across the day, with a slight peak in the evening coming down overnight. But this is rapidly changing as we're seeing more and more grid level technologies coming onto the grid. We're seeing the solar duck curve come about by the increase in rooftop solar coming on board. We're seeing the camel's humps of the electrification of heating as people are moving away from gas, moving more towards electrification technologies and heat pump technologies. And then we're seeing the giraffe's neck of the EV transition. So we're seeing two things at play here. We're seeing a much peakier energy usage curve, and we are also seeing a much higher overall load in electrification. This is going to get increasingly worse over time. We're at 40 million distributed resources today, and that's been predicted by Bloomberg to grow up to 200 million devices by 2023. By 2030, across a range of different technologies and a range of different countries. This is being brought about by the reduction in cost, as well as government subsidies at the local level. We've seen the Inflation Reduction Act here in America, bringing down the cost of technologies, and we've seen that globally at scale too. And this is where we think the technology can play a key role to it. Another sporting analogy, apologies. On the left-hand side, you see Jesse Owens, who is the American Olympian who broke 3 world records in the 1936 Nazi Germany Olympic Games. And on the right-hand side, you will see Usain Bolt, who I'm sure all of you were familiar with, who currently holds the 100-meter world record in 2009. People are probably thinking, what's the relevance here? Well, the difference between those 2 world records 73 years later is 0.62 seconds. And it's come about not because of human change. Humans haven't evolved that much in 73 years. Change has been driven by technology. Change has been driven by changes to the springs at the start of the race, changes to the shoe technology, and changes to people's nutrition and diet. And this is where technology can have a real impact across a number of different areas, and where it can really help with the energy transition. So there are 4 key areas that technology can help to deliver disruptive change. So a lot of the good news is a lot of the technology that we need already exists. We're seeing EVs coming on board. We're seeing heat pumps coming about. Lots of batteries involved as well. So the 4-step change. Firstly, we need to connect everything. We've already talked about 200 million connected devices coming online by 2030. And as well as this, there's going to be increasing problems that come about by the proliferation of different makes, different models. We're seeing EV companies bring out lots of different types of models. We're seeing existing, traditional gas car manufacturers bringing on board new EVs, and we're seeing new brands come about across the globe. We're seeing an increase in different standards being adopted by different territories, and we're seeing that OEMs are also having different platforms across different geographies. This makes it really challenging, but it's something that we really do need to overcome. We need to work together with all of these OEMs to connect their devices, unlock flexibility, unlock savings from customers. I think the good news is that we're getting a lot of them on board. I think we've heard a lot at the conference over the last couple of days that there is value from these connected devices. But if we don't do anything about it, the system is going to struggle. Next thing we need to do is to digitize the distribution networks. This is a light map today of the USA. Very easy to see what's happening everywhere. You can see areas of congestion, you can see areas of intensity, and you can see areas of underutilization. This makes it very easy to see when issues do arise. However, in reality, only 5%, when it comes to the grid edge, in reality, we can only see about 5% of the network at the very last stage. This is a light map back from the 1950s at a time when the networks were built. And this is what visibility looks like today. The engineers that built them back then built them very well to handle the worst case scenarios, and so visibility wasn't needed at the time. Historically, close to nothing was being consumed and generated. Nothing was being generated and consumed at the grid level. It was all done at the large scale level. But now, with the proliferation of devices, the devices set to move to 200 million by 2030, this is only going to get worse. We need more and more visibility on the network to ensure that we can understand what's happening and plan around these to avoid any congestion. We know that we know the potential from the changing use curve that we've seen in the proliferation of devices, that we're going to need large scale kind of infrastructure upgrade to be able to handle these. But this is where we believe that technology can really help to light up where those problems are, understand what's happening on the network, and to optimize those devices to effectively avoid some of the larger scale upgrades or delay them in time. The good thing is we've already got a huge amount of rich data that sits at the grid level that we should be able to utilize. We need to be utilizing this data in conjunction with some of the kind of larger scale network monitoring that we're putting on place. There's loads of devices on the level. We as a platform are collecting 3 billion reads of data a day, 35,000 reads a second. We need to use these data points to create these light maps, understand where congestion is happening, use it to forecast congestions, develop signals from there, and optimize based around that. That's all very well said and done, but actually the key thing is the consumer at the end. The consumer is the one who have these technologies in their households, and the consumers are the ones that we need to take on this journey. We know that consumer flexibility is going to be a big key tool to the energy transition. In the UK, between 2021 and 2050, we're going to need 12 times more non-thermal flexibility. I know a lot of people say that math doesn't add up, but the fact is that we've got a lot of thermal generation coming offline in that period. We believe that over a third of this is going to come from customers. Customers are going to have to play that key part in the transition. But first of all, we need to understand what consumers really want. We're moving more towards this era whereby consumers are getting these technologies. We're moving out of that kind of early adopter phase. We need to really understand how can we take customers on that journey? How can we make them part of the transition without impacting their everyday life? And first of all, we've got to understand what they want. EV drivers, what do they want? They want cheap range when they need it. They want their car to be at the state of charge that they want at the time that they need it in the morning. And they want to pay as little as possible. People are going to start making purchasing decisions based on the rebates, based on the tariff structures that they can get for using their car. They're going to start comparing that plans available to miles per gallon. When it comes to solar and storage, what am I getting back for it? How can I increase my return on investment? How can I bring back my payback period? And when it comes to heating and cooling, what do I want? Again, it's a large part of my energy bill. I want my home to be at the right temperature at as low as cost as possible when I'm there. But again, the energy sector typically today has been one that's highly distrusted. People wait long wait times on the phone. People have expensive bills, and it's something that nobody wants to have to deal with. And this is where we have to use the tools to effectively create these customer offers, take these benefits that we're seeing from technology, from optimizing across the network, taking cost savings from infrastructure upgrades, taking cost savings from moving when energy is consumed, and putting them into simple customer experiences. Make it very easy for customers to connect their devices, understanding what's happening to their devices, but also keeping them fully in control. This is an example of an EV proposition where you can see that a customer can simply connect their car in their utility app. They have all of the tools that they need. They can effectively set their charging limit, set their ready by time, and view the schedule that's going to change overnight. Again, they can change any of those preferences. It'll create a new charging schedule based on the optimization algorithms that go into it in the back end. So here's a use case of a customer that's fully in control. There's no disruption to their day-to-day living, but by being able to have that control in the back end, we're able to extract the savings that come and pass this back to the consumer in the form of lower retail offers, rebates, customer saving them hundreds of dollars a year on their charging. And we've seen this happening at rapid scale in the UK. We launched an EV proposition back in January 2022, connecting up to 600 devices, growing to 25,000 devices by 2023. We're now just about to go to 150,000 devices, proving that when you create these simple customer experiences, past those savings that you get back from those optimizations based on the optimization schedules you can do back to the customer in the form of lower plans. And then number 4, and I think it's a key theme that we've all been seeing across the conference over the last couple of days, is optimizing across the whole system. We need to make sure that we are effectively not optimizing our siloed models, but looking across the entire system, providing tools to enable this optimization to happen across the entire energy system, to ensure that we are helping accelerate that transition as fast as possible. Again, a lot of that is down to market structures. We also need to provide technology to do it. The use case in the UK is they have 150,000 EVs, working very closely with the regulator, the network operator, to effectively participate these domestic assets into traditional markets with the balancing mechanism to effectively help enable that kind of system stability, extracting value and passing these back to consumers. So those are the 4 key tools. I think the key takeaway is we can no longer rely on the incremental improvements. We need to think and act differently. It's coming. We're seeing these devices grow at a quicker rate than we've ever seen before. There are plenty of problems that this can bring about, but actually, if you can get it right, if we can bring consumers on that journey, we can make them part of the solution and not necessarily the problem. Thank you.
Excellent. Thanks, Tom, for that great presentation. Our third speaker is Brad Smith, who's the Smart Energy Lead at GRIDSIGHT, which is in Australia. Thanks also for making the journey. He's going to be talking to us today about dynamic operating groups.
It's Bryan. Yeah, good morning, everyone. Thanks, Greg and Tom, for two great presentations. I think they really set the scene for what I'm going to talk about today, which is really a bottom-up way of modeling a distribution network that then enables optimal decisions to be made about customer or dispatching or controlling or optimizing customer energy resources that produce an optimal or an impact at an aggregate distribution system level. So glad you keep that in mind through the presentation. The way we want to go through that today is to provide a very brief background on GRIDSIGHT, what we do, really setting the scene for what we're talking about or the method that we want to go through today. Give an overview of the Australian DER landscape. That's important because it sets a key driver for really why we exist today and how our techniques are appropriate to that. Provide a solution of what we're doing, contrast that with the traditional approach, then go into some results and future work. So at GRIDSIGHT, we do quite a few things, but I think the most succinct way to probably describe what we do is we're providing visibility, insights, and optimization, typically where SCADA ends. So in an Australian context and working here, seeing a very similar thing, that's typically at the MV feeder outlets of zone substations. There are some exceptions, some recloses and smart distribution substations, but generally speaking, we're trying to fill that void by leveraging data primarily from smart meters. So in terms of the Australian DER landscape, it's pretty well known and acknowledged, but some numbers I'll go through you may have heard before. There's about 20 gigawatts of installed capacity. Bear in mind, Australia is a nation of only about 26 million people without crazy amounts of energy density. So that represents actually really quite a high proportion of installed capacity. Overall, there's about 1 in 3 homes in Australia have rooftop solar, and in South Australia and Queensland, which is the brown down the bottom is South Australia, and the yellow along the northeastern coast is Queensland. It's up to about half. The brown state, South Australia, actually is increasingly recording reverse power flow out of the distribution network, which is flowing onto the transmission network. They're also at the end of our interconnected national grid. So when the interconnector from the brown into the purple is functioning, that's generally fine. There's been a number of instances though where that interconnector's gone down, and now that amount of excess solar is causing some real stability issues. In addition to that, there's also localized voltage and thermal constraints that this penetration of solar is starting to bring about. This slide here really goes through the standard approach that's kind of been taken to date in an Australian context, and that's introducing a static export limit at the customer level. So that's really quite a dumb solution in the sense that it's a local control, it's static. There's a clip-on CT that's typically put on the meter, and that's just limiting what the inverter is doing such that it can only export all the time at a very fixed limit. That little dash line below there kind of shows the amount of foregone energy as a result of that. So the amount of energy that could have otherwise been provided by that distributed resource, but wasn't as a result of this scheme, and that's in place all the time, regardless of what's happening either locally on the grid or at a macroscopic level. This slide here then illustrates the difference between that static limit and what a dynamic limit can do. So the dynamic limit is the tan or sort of green line at the top. What that's showing is that limit will only enact when it needs to, generally based on either a localized voltage, thermal, or also some type of system level constraint. A key thing to note there as well is the difference in the amount of curtailed or released energy. So the difference between the blue line, the difference between where the blue line is and the tan line and that energy in the red line is really the released energy under a dynamic operating envelope setting. So it's only curtailing that amount of blue when it needs to, whereas all of the blue above the red line is gone, the static limit. Probably worth noting as well, 5 kilowatts is one of the upper export limits we're seeing in Australia. What is actually starting to happen increasingly in Queensland and South Australia is even more aggressive static limits of 1.5 and even 0 kilowatts of export. So in terms of what we can do about that, or in terms of constructing that dynamic line, I want to go through at somewhat of a high level what our methodology is to do that. But probably important to note as well, this framework or this architecture methodology, whatever you'd like to call it, is not just applicable for solar export dynamic operating envelopes. It really can apply to optimizing any type of customer resource to produce sort of aggregate system level outcome that Greg and Tom spoke about. So the recipe, if you like to do that, is we take input data from our network customers. That's generally smart meter data, as well as some form of just hierarchy mapping. So mapping how those N meters map to distribution transformers. Importantly, we don't need conductor and impedance information. We don't need people to have mapped all of their network and recorded perfectly all of their conductor information. The reason for that is down the bottom. We're not running load flows. We're using a technique that's model free, which I'll go into in the next few slides. What model free means, the name is a little bit of a misnomer. I and our colleagues don't really like it. What it means is you don't need an electrical model, but we certainly still are producing a model that relates power injections to voltage in the same way that a load flow does. So in addition to those two input pieces, we take network constraint limits, so voltage, thermal, they can be system limits. We also take objectives, like in any optimization. Putting all of those together, we can then devise a set of optimal or near optimal signals that can be dispatched to end devices, or really any device that's in a network, but particularly distributed end devices, in order to try and achieve that objective. So this slide here is really trying to just provide a little bit more context on what I'm talking about today and where we kind of sit in the overall stack. So at the top, you've got the DSO, there's their traditional systems, SCADA, ADMS, all that sort of stuff. We're then ingesting data from AMI, GIS, and PQ. So we get that from our distribution partners typically. We combine that with third-party weather data. We devise signals, and then we send those signals out to via a communication layer. So we're not looking at interfacing directly with end devices, but partnering with DERMS, aggregators, other hybrid architectures to pass those signals down. I guess from our perspective, it's really important to have something meaningful to tell an end device, as opposed to it's not our role to try and solve the challenge. A lot of people already are in how you get those signals out there, but we're very conscious of, if we're going to talk to something, particularly if it's a piece of customer's equipment, that we're telling it something very meaningful or very impactful. So it's many in the room, and as an engineer, I really wanted to include some equations, so we got one in. This is a traditional approach, I guess, to modeling networks. You take a network model, you take the impedance of all cables and conductors, the length of line segments, the impedance of the transformer, you try and map as best a phase allocation or distribution. A really tricky challenge is to then get the load and generation for all customers. Typically, we see archetypes used, paradigms, big assumptions made on the loads. And so even if you have all the other stuff perfect, that assumption often produces pretty suboptimal results, particularly at the LB level, where you don't get the nice averaging that occurs as you aggregate things up. And the final thing I'd say about load flow is it's really quite time consuming to execute. It's computationally expensive. And often you don't have a way to evaluate how accurate that model is before deploying it. State estimation and other techniques obviously work through that, but again, they're quite computationally expensive. So the approach with model free that we take is to contrast that. Utilizing historical data, we use a machine learning model to train what those voltage and current dependencies are. As part of that training process, we can then evaluate how effective the model is. So like any supervised machine learning process, we're able to separate the data and then evaluate how good that model is. we're doing that on a distribution transformer by distribution transformer basis. So once we're able to evaluate those models, we're then able to deploy them, and then they're highly performant. Once the model is trained, once you provide it data, it's able to produce outputs very quickly, which then naturally form a nice basis to run optimizations over the top of. So in addition to the use case I'll go through today, this then forms a basis for a set of use cases. So assessing new DER connections on a case-by-case basis. So that simulating if 5-10 kilowatts was added to this point in a network, will it create voltage excursions or any thermal issues? Deriving general network hosting capacity, so we can apply somewhat the same optimization framework, but in a slightly different way, and from that derive how much hosting capacity is available on the network. That can then feed into a whole host of scenario planning in the longer term sort of studies that Greg spoke about. And then what we'll go through the results of from a couple of studies we've conducted. 2 of our utility partners now being dynamic operating envelopes. Final thing about Model 3 is it's not just voltage. We're also looking at calculating. We're also inferring the unknown load, which of course is very important in any sort of network analysis. So what you're seeing there is in a sparse metering environment, and typically in a non-Victorian Australian context, Victoria being a state, we have about 30 to 40% meter penetration. So that purple line is meter sums at the distribution transformer level. The orange line is our estimate, and the blue line you're seeing is, this is from a substation with the transformer monitor, where we can use that as a bellwether to compare with our estimates. So I mentioned that we have a model of this per distribution transformer. So this slide, I won't dwell on it too much, but we set up quite a sophisticated data pipeline, which enables us to train in a distributed way at scale, and then importantly evaluate the models in an ongoing basis. And so we can identify model drift or topology changes, new additions to the network, really anything that's going to affect the outcome of the model. So pretty important point in that we're not just training once and then thinking that that model is going to do its job forever, but as part of our pipeline, we're constantly evaluating the efficacy or accuracy of that model with each run. So that's the method. What I want to briefly go through now is the results from studies we've done with 2 of our utility partners. Important to note, these are studies that are basically looking back over a period of data that's typically around a year. So we've simulated what a DOE could have done, comparing that with measured voltage and exported power. We've done that for 2 DSOs, Endeavour Energy in Australia and Energy Queensland. So if you recall the other slide, basically the eastern coast of Australia they cover. 4,516 models have been trained. Of all of those, the root mean squared error of the voltage prediction is about 1 volt. The max error we've seen is 6 volts, and the average meter penetration is around 40%. The graph on the right there shows you how the Model 3 is tracking on a time step by time step basis versus the blue, which is the actual measured amount. Slide just provides some details into what was put into the actual optimization. So the key things there, the objective is to maximize exports. So only curtail when you need to curtail. The constraints, there's an upper steady state limit in Australia of 253 volts. That can be set to whatever is appropriate. The thermal constraint is that the aggregate exported energy should not exceed the kVA rating of the distribution transformer. And the customer, the min amount that we curtail to is 3 kilowatts, and the maximum allowed is 10. Importantly too, there's 2 allocation methods. Optimal being solve, basically provide the minimum amount of curtailment that will achieve the objective, even if that means certain customers get curtailed more. Equitable means that everyone will get the same proportional curtailment that occurs, which generally leads to over curtailment. And there's a lot of debate around, is equitable actually equitable if everyone loses? This screenshot here is really just showing where those circles are. The upper arrows in red are showing where there was measured voltage excursions, and the graph down the bottom, this is at a distribution substation level, and then the graph down the bottom, which I'll go to now, is showing what the DOE did in that situation. So This is at an aggregate level. You can see the tan and purple lines are the DOE's binding to avoid that voltage constraint. And then you can see the amount of curtailed energy between the blue and those shaded bands for each spin. This is showing for the worst case voltage. So the customer that had the worst voltage excursions in blue on that particular substation, the result of that curtailment. So you can see the tan line, which is what the predicted voltage is that we optimize against, holds flat under that period. So it's really showing what the effect of, from a voltage perspective is on performing that curtailment. A little bit hard to see, I acknowledge that. But on the far right, what we're doing then is we're accounting for that curtailed and lost energy and the percentage of time that customers are curtailed under both schemes for each distribution substation, and then aggregating that across the whole network. The key metrics are the columns on the right too, which is how much energy was curtailed, but then importantly, next to that is how much energy was actually released compared to a static export. This slide then shows basically graphs that amount of released and curtailed energy as a function of the PV system size for any systems that were curtailed over that year across the two networks. Very important to note that 85% of systems actually didn't experience any type of curtailment. So the numbers you're seeing here are for the 15% of systems that did. Then as a function of the PV system installed capacity, what was the average amount of yearly energy in kilowatt hours that was released as a result? So you can see for as expected, the larger the system size, the higher the magnitude in that energy. And for a 10 kilowatt system, over that year, we're sort of talking about 5 megawatt hours of released energy under an equitable or optimal scheme, compared with that small amount of curtailment down the bottom. So it's kind of the takeaway, big takeaway from my perspective there in terms of the actual impact, both at a customer and system level in terms of how much extra energy can be released by implementing this. We're moving into a real-time trial. So what we did was batch, but won't dwell too much on this. Probably the biggest point I'd make here is beyond the obvious, with data actually streaming in and signals being sent in real time, providing an ability to send what the set point was and track, did a system actually respond to that? So we're very aware of evaluating the system may claim to be DOE ready or DOE compliant, but this helps track, is it actually responding? And finally, the future stuff we're focusing on beyond just solar export limit DOEs is import limits for EV charging. So basically only curtailing the amount of charge when needed. It's not directly changing the profile, but just curtailing when needed. Scaling to real-time optimization, exploring opportunities in other network architectures such as the US, and the inclusion of minimum or system level demand constraints, so not just localized thermal and voltage. Yeah, that's it from me. Here all day, so love to chat to anyone that's interested. Cheers.
Thanks, Brad. That was great. Our last presenter is JP Carvallo from Lawrence Berkeley. He's a research scientist. He's going to be talking to us today about advancing the reliability of distributed PV plus storage.
Right. Thanks, Brian. Thanks, everyone, for staying in. I think I'm the only thing standing between you and lunch is me, so I'm gonna try to be brief.
We got time for questions too. So.
Oh, good. So
I'm not totally.
Yeah, everyone's a lot of pressure. Thanks, Brian. Thanks for reminding me that. And apologies for the folks that have to see me for the second time up here, but I'm filling in for my colleague Will Gorman, who is the technical lead for this particular study. He couldn't be here today, and since I was coming to ESIC anyway, he asked me to present as a co-author. So any errors in the presentation, of course, is Will's fault. Yeah. Let's see. So I wanted to situate this presentation in particular in the context of this panel. You have been seeing we've been coming from the systems levels analysis in terms of value of DER across the entire value chain, and we went down now to a focus on the distribution system with Brad. And now we're going to go inside the customer behind the meter, and we're going to understand one particularly understudied value element of distributed resources, in particular solar plus storage, which is the resilience value. Yeah, as you saw in the presentations, they typically refer a lot to the energy value, the capacity contribution, some ancillary services, and voltage regulation. But we have understudied the reliability and the resilience contributions of these resources, and we're going to see this from the perspective of the customer in this presentation. So one thing and one obvious reason to do this is that we're seeing a substantial increase in what we call the storage attachment rates. This is how many customer-sided solar systems are also adding storage, either from the onset, so systems that are deployed as hybrids, or are adding storage to an already existing PV system. And we're seeing, based on our latest analysis, that this is reaching about 10% of installations. Hawaii, not surprisingly, has by far the highest attachment rates in the US. Over almost every customer that has a solar panel in Hawaii has also a storage system, and that's because of the particular incentives by net metering reform that exists there. But also in the continent, California, that also hosts the most paired systems and has attachment rates of about 11% for residential customers. So what we do know is that one of the reasons why the customers are adopting storage behind the meter in the continent, but also in Hawaii, is because of concerns about reliability and resilience. The grids in several parts of the country have been suffering with more interruptions and longer interruptions, especially because of extreme weather events, and that's in general only going to get worse. And so we have many customers, perhaps unfortunately so, customers that can afford the systems, to add storage to already existing solar systems. Now, there are new incentives by the Department of Energy that are coming in to help other customers also acquire these systems. So we'll probably see a growth of these. Understanding the backup power capabilities of behind the meter solar for storage is important to inform customer investments. And for the customers that have adopted, we can sort of infer that their internal value of those load was higher than whatever the cost of that unit is. But there is a wide range of customers that may be deciding whether to include storage or not in their system PV systems, and knowing what are the resilience and reliability benefits of the system would make this potential investment decision pencil out. We're also interested in studying how the solar plus storage systems will perform in both the current building stock, so the current set of end uses and types of buildings, but also forward-looking. Over the next decade, we expect, as many people have said already, a number of electrified end uses to come into the homes, and potentially a number of retrofits on the buildings themselves, both of which may affect what is the resilience and reliability value. And I'll stop and sort of quickly point how I'm using resilience and reliability in a very specific way. Typically, the way we understand it, we call resilience the ability of the systems to mitigate long duration, widespread types of interruptions, typically more than 24 hours. And we call reliability benefits the ability of the systems to mitigate short duration, typically random or unpredictable interruptions that occur largely at the distribution system level. While our work has actually examined both, I'm going to focus this presentation on the former. So to set this up, we develop a pretty thorough treatment, data-driven treatment of how solar plus storage would perform by bringing in a set of end-use load profiles from NREL's Restock tool, and also solar profile productions from the system advisor model, also from NREL, and couple this with a set of synthetic and historical long-duration event interruptions. So in this particular case, we're not saying how often these interruptions are going to occur. We're just going to examine how does the system behave if a one-day interruption hit, a 3-day or a 10-day interruption hit. And we also did an analysis based on existing events, 10 actual events that occurred over the last few years, and understanding how would homes have fared should they have had solar plus storage system installed with these particular historical events that occur with particular weather conditions. So we blend all this in a storage dispatch model, and we're trying, and based on a number of assumptions about the PV size, the event start daytime and duration, the state of charge of the battery, and the types of loads that need to be met, we can determine how much of the different types of loads can be met in terms of percent of the total load. And the minimum, we also recently developed the ability to also determine what is the size of the battery that you need to achieve certain outcomes in terms of resilience results. As I mentioned, we're doing these two analyses. First, the baseline conditions, which are done for the all the counties in the continental US. I'm going to show a couple of results for those, but I'm going to be focusing mostly on these specific future load conditions, for which we select 10 counties that have a range of climate conditions, and we test 4 specific type of scenarios. We set a flexibility scenario where we allow the set point in the thermostat to be variable. We allow for an envelope efficiency retrofit, heat pump retrofits, and other types of end-use electrifications. And we test how the battery size and the mitigation potential of the PV plus storage system varies with all these combinations. In terms of loads, we have typically 3 types of analysis. We have a set of limited critical loads that are what we have seen are what customers really want to protect when they are acquiring backup systems. We have what we call critical loads, that is the limited critical loads plus heating and cooling equipment, which we analyze separately because it's such a large load, especially when you're electrifying heating. And then we have the whole home. So I'm going to share some results out of this work. What we see in the case of the baseline buildings at the national level, these are about 3,000 counties in the continental US, and we see that in general, the backup performance is pretty good across both seasons, but it does vary significantly in terms of geography. When we include heating and cooling in particular, there is a significantly lower capacity to serve load compared when we don't. And this is particularly true, as you see here in the chart, towards the southeast US and portions of the Northwest, both of which have significant amount of electric heat and resistance heating. The performance tend to be lower in the winter months because of the same reason. And in the summer months, it tend to be worse or more complex to handle large cooling loads in the Southwest and the Southeast. And of course, it's not surprisingly that the performance is also lower when we're doing a whole home backup. And which is interesting here, this is the result, by the way, for a 3-day interruption, is that there is, for many customers, they will be able to meet the entirety of their load needs. But for many of them, for many other customers, they will be able to meet probably 20 or 40% of their load. So that shows that there is already a wide range of mitigation potential for a system that is sized according to the load, but whose performance depends significantly on the types of end uses and the location. Analyzing the types of for historical events, the important part here, the important aspect that we want to capture is that most of these events that you see here, and the folks from the US in this room will recognize a lot of these storms and events, in particular, or the California ones will recognize the PSPS, the power shut-off events that occur in a preventive fashion. These are all occurring within certain types of weather patterns. And so it's important, we want to capture how the particular behavior of the solar plus storage system in these particular weather patterns. And in general, we find pretty good behavior with the exception of a couple of winter storms where, again, the winter storm happened in a place that has relatively large electric heating, and we see lower levels of backup. When moving to understand the required battery size to achieve certain outcomes to mitigate the whole load, we find interesting results. And we did this only for these 10 counties that we selected, where we had a combination of specific end uses and locations. And what we're finding is that for the baseline building stock, the cycle of batteries to mitigate the entire load, the entire interruption for these critical loads that include heating and cooling range for about 10 kilowatt hours in LA, all the way up to 90 kilowatt hours, which is probably 5 or 6 times what a traditional battery size would be in a residential customer. So that reflects the challenges that exist when we're trying to back up loads that include electric resistance heating, and how it's a little bit easier to do this in places that have more temperate weather. Now we're going to move into understanding the second part of this work, which is how does the battery sizing of matters when we have certain types of distributed resources that are being acquired. And so what this is showing is how the incremental addition of specific types of measure bundles change the battery size. And what's a couple of things that are interesting here is that in places that have a fair amount of electric resistant heating, like you see here in Phoenix, or Dallas-Fort Worth, as we add these efficiency measures and including the thermal set point adjustments, building efficiency and heat pump retrofits, we significantly lower the size of the required battery. In contrast, in places that have fossil fuel, especially when we do the substitution from fossil fuel heating to electric heating through heat pumps, the size of the battery, of course, jumps significantly. And this is something that has been discussed already in how moving away from gas into electricity will pose significant challenges for homes that want to keep doing backup. And this is including management of the set points and being smart about the way we use those heat pumps. It's still the size of the load just imposes significant challenges for maintaining and meeting the heating needs. We try to understand if we were to now think about markets that can, or customers that are willing to purchase up to 30 kilowatt hours of storage, what can we do in terms of the different retrofits to try to, how many homes will we be able to have full mitigation of their critical load plus heating and cooling with just 30 kilowatt hours, accounting for set point adjustments, envelope efficiency, and heat pump retrofits. And what we found is a combination of these can raise an addressable market that is it's ranging from a low 6%, for example, in Phoenix, to a high 90% in LA. It can raise it up to about 60% in all 10 regions. So this attests for the relevance of using in conjunction with the backup, or it sort of reflects how important it is to include these other types of distributed resources like set point adjustments, envelope efficiency, and heat pump retrofits in order to create a market that is addressable with the current size of batteries that it's typically no more than 30 kilowatt hours. Finally, I'm going to talk about a few sensitivity analysis, and this is where I'll say that the full report includes probably dozens of more results and analysis that I'm showing here. In particular, we have a whole different track that is examining reliability. So if we develop a model that can produce random short duration interruptions across the country, and we can test how the system performs in those. But in this case, one sensitivity I wanted to share is the fact that there are interesting outcomes when the interruption occurs in terms of the net load percentile. So the interruption can occur anytime in the month, right? And this 3-day interruption. And it could occur right at the point where we have the highest demand for some reason in that particular month, or it could occur where we have a low demand. And as you see here in the different colors, not only depending on the location, but for any location, the difference between interruption occurring in a low load day and in a high load day is pretty significant in terms of the battery size that I need to mitigate an interruption. This is something, for example, if you look at Dallas-Fort Worth, is rather extreme, where you need less than about 10 kilowatt hours to meet load when you have a low load day. But if you are having a high load day, you need a 150 kilowatt hour battery. That's really a garage full of batteries. So it attests again to the relevance of doing types of demand response and demand control. And to the right, we have implemented those measures, and it becomes evident that at least some of those places are able to curtail the size of the battery needed to mitigate load needs, but still the sizes are significantly higher when the interruption occurs in a high load day, especially in the 95th to 99% load day. And again, we don't have a good solution for this, but it shows how hard it will be to meet all loads for customers that even have, or unless the customer have substantially larger batteries that I will say might not be economical, given that these are occurring in just specific times of the year. So as a conclusion, what we're finding out in these 2 years of analysis over the residence value of solar for storage is that the required battery size will vary considerably across individual homes, across locations in the country, and that this sizing will depend highly on the timing and duration of interruption. Or put another way, if you wanted to insure yourself against any type of duration and any type of timing of the interruption, you will require a substantially large battery that most likely might not make economic sense for many customers. Now, having said that, we have just started doing some economic analysis in our third year of analysis for this work. And we are trying to include other value streams for these storage units. For now, all of you have seen is the resilience value, is their capacity to mitigate loss of load. But there are, of course, as other presenters have shown, other value streams that can be valued in the market and can add to the benefits for the customer. We're showing that low flexibility and building envelope efficiency can have an important impact in reducing the needs for storage size, but that in regions with large cooling or electric heating loads, it remains challenging to meet all required loads. In particular, the impact of heat pump retrofits, and this is an important analysis because we're just starting to see more heat pump adoption across the country. Battery sizes to be able to supply heat pumps during times of the year will depend significantly on what exactly the heat pump is replacing. If it's replacing a fossil fuel, the size of the battery will drastically increase. If it's replacing an electric resistant heating element, then the size of the battery can go down because of the efficiency gains. Finally, we also find that other forms of building electrification, for example, cooking or water heating, those have minimal impacts. I mean, the size of the loads are quite lower compared to space heating and cooling. So we don't end up finding that it have a major impact on defining battery size. And we didn't analyze electric vehicle charging in a V2G fashion and how that battery can actually supply a portion of what these larger batteries that are exclusively designed for solar period could do, but I didn't have the chance to include that in this work. So finally, I wanted to wrap up with some implications for utility. So this is all happening behind the meter, but there are interesting lessons coming out of this work for utilities. For example, the methods that we have developed can be useful to apply in front of the meter as well, to understand the benefits of batteries and solar plus storage systems to mitigate interruptions. It also serves to understand how the potential drivers for customers to uptake storage, to invest in storage, and to use it in certain ways. So in general, we are assuming here that the customers have their battery topped up when the interruption hits because it is a long duration interruption. But in general, the customer will be using the battery in some way, and we can use these methods and models for that. And finally, we can also use the method that we're designing here to price the reliability and resilience services of these units and start thinking about compensating customers for those, or if virtual power plants want to bring them to the market, we can provide a value for that. Thanks so much. This is our contact information, and thanks for our works as well.